Thanks for giving me the chance here to talk about multi-GPU programming with MPI and Nickel. I assume that most of you are familiar with MPI in some sense, so I just put together the pieces, what's missing there. So, and what I'm mostly talking about will be CUDA-AWARE MPI. So it's a very simple mental model is we have a cluster with multiple nodes. In each node, there's at least one GPU, and the GPUs solve a problem together cooperatively using MPI as a programming model. So as you all know, then you need to exchange data to communicate between these models so that they coordinate their work and actually contribute to the same problem. And when you know how to program GPUs and you know how to program MPI, there's really not much more I need to tell you, because with the CUDA-AWARE MPI, things just work as expected. You can pass in device pointers directly into the MPI routines of the CUDA-AWARE MPI, and MPI will do the right thing and move the data correctly, also exploiting acceleration technologies such as GPU-direct RDMA or peer-to-peer to use direct NVLink connections within a node or direct PCI Express connections to network adapters. Of course, there are a few more things that are worth sharing, and that is the intention of my talk today. I will use a very simple example, what I kind of describe as the hello world for HPC, a JACOBI solver, solving the 2D Laplace equation. You don't really need to follow the math, just giving it here for completeness. And to show the most common communication patterns, I'm applying for this 2D problem, I'm applying 2D domain decomposition. Okay, to get everyone on the same page, how does that look? So we have a iterative process where we iterate until we have converged. And in every iteration, we execute a JACOBI step where every part of the domain, each GPU processes the interior part of the domain, updating an new array with essentially the average of the neighboring values from U. And after that, we need to propagate information across the whole domain by exchanging our halos with 1 to 4 neighbors. That means that we need to update their halo values, which is a replication, that's always a replication of the neighbor's interior domain. So the leftmost, the left halo of this domain is a replication of the rightmost interior column of that domain. The upper halo of this domain is a replica of the last interior row of that domain. And by updating this after each iteration, information propagates across the whole domain, and all GPUs together solve the program cooperatively. Then we swap the roles of U and UNew and start the next iteration. So, as said, for brevity expressed with MPI send receive, that if you know MPI, that works as expected. You pass in the references to your device memory for the communication. And in a first communication step, you send, for example, that's one way to orchestrate the communication. You send the first row modified, each rank sends the first row of its interior domain to its top neighbor, and at the same time receives from its bottom neighbor the last to its halo, to its bottom halo. And in the second step, then each rank sends the last row of its interior domain to its bottom neighbor, and at the same time receives from its top neighbor to its top boundary. And yeah, that is just basic MPI and domain decomposition. What I want to highlight here, if you're using CUDA, C++, CUDA, you just pass in the pointers you use in your kernel, so where the data is current, and MPI will take care of moving the data in the right way. The same is true for if you're using standard language parallelism, here as example ISO C++. In this case, you just pass in the data you're working with, because there is only a single pointer, and CUDA-AWARE MPI is also able to handle the unified memory, which is the backing technology for all the allocations with standard language parallelism. With OpenACC, there's something you need to take care of, because there you only have a single symbol, UNU, and in an accelerated program, there's two representations, one on the CPU memory and one on the GPU memory. And usually OpenACC can derive from the context which representation to use. For example, if you launch an OpenACC kernel, it knows that it needs to use the device pointer behind that symbol and not the host pointer. But if you're in CPU code, like you are when doing MPI calls, it derives from the context that it should use the CPU pointer. And in this case, because all the computation happens on the GPU, MPI send receive would exchange state data, and the simulation would not progress. And OpenACC provides a directive to instruct that in this case it should be different, and that is the Pragma ACC host data use device directive. And in the following scope, all variables listed, not the CPU pointers of the symbol are used, but the GPU pointers. So that this as the CUDA-AWARE MPI gets the pointers to the data in GPU memory where it's coded. So that is effectively communication with CUDA-AWARE MPI, OpenACC, CUDA C++, and ISO and standard language calls, for example, ISO C++. And then that all the necessary data movement is handled by CUDA-AWARE MPI. In contrast, if no CUDA-AWARE MPI would be used, the MPI would only be able to handle CPU memory. In this case, the standard language parallelism cannot be used reliably, because if the MPI is not aware of device memory, it's also not aware of unified memory and its properties. So things might work and you're lucky, but it could also happen when using unified memory with a non-CUDA-AWARE MPI that you get silent data corruptions because state data is sent or so. So therefore, only CUDA and OpenACC here. In both cases, because the MPI can only handle CPU data, we need to copy the data we want to send from the GPU to the CPU before we do communicate, and copy the received data back after we communicate. In CUDA, that's done with memcopy, and OpenACC with the Pragma ACC update host for the device to host transfer, and update device for the host to device transfer after the communication finished. So nothing you should do, just to highlight the benefits of for code simplicity besides performance of CUDA-AWARE MPI. The left-right high-low is something I have not covered, and an important thing I want to point out here, you could, of course, that the implementation of MPI data types in CUDA-AWARE MPI is, in the CUDA-AWARE MPI implementations I'm aware of, is functional in the sense that it's correct, but I would say in many cases has practically unusable performance. So what you need to do, you need to pack your non-contiguous data along the non-contiguous dimension of the domain manually on the application side. And that is a process that gets much faster in device memory. So you should do that packing in device memory. With standard language parallelism, again, ISO C++ as the example, that would be, for example, done with a parallel for each and using the parallel unsec execution policy before doing the communication of the non-contiguous data to a contiguous communication buffer, then communicate with contiguous communication buffers, and after communication finishes, unpack the data. With OpenACC, the concept is very similar, just using OpenACC to express the parallelism. So we have packing with an OpenACC parallel loop before communication. Again, we need, of course, to use host data use device because we have packed into a device array and need to communicate with that. And after communication finished, unpack with a OpenACC parallel loop on the GPU. Again, same context with the concept of CUDA, just that we, of course, need to launch kernel for packing and unpacking. And because their kernels are asynchronous, with regards to the CPU, we need to remember to synchronize our backing kernels before we start the MPI communication. Okay, so then next, a few other things you probably need to know. There are two more aspects you need to know when using CUDA-AWARE MPI for your MPI plus OpenACC CUDA standard language parallelism, however accelerated program. And one is that some CUDA-AWARE MPI implementations require you to enable CUDA-AWARE features at runtime. First of all, of course, they need to be built with CUDA-AWARE support. That's omitted here, but some of them also require to set an environment variable. For example, MPI requires to set mpitch RDMA enable CUDA, MB pitch to set MB2 use CUDA equals 1. And a few are listed here. If yours are not listed, please consult the manual of your CUDA-AWARE MPI you are using. Otherwise, the application is exactly launched as you're used to. So I'm just using here MPI run as an example, because that comes with most MPI implementations. But if the system you're using uses, for example, a Slurm workload manager, that it equally well works with srun. And so the spawning of MPI process is no different from CPU MPI programs. Another aspect to consider is that usually GPU affinity is handled by the application and not by the launcher. So if you, for example, consider a system with 4 GPUs, 4 nodes, and each node has 4 GPUs, and you launch 1 MPI rank per GPU, as it's most of the time the best thing to do, you end up with 4 processes per node, and they have ranks from 0 to 15, and, for example, could be placed like that. Now the question is, how does each rank decide, because the only information it has is its MPI rank. How does it derive which GPU to use? Should it use device 0, 1, 2, or 3? Might be optimal, might be obvious for the first node, but not for the second. Now you could rely on that ranks are placed consecutively by your job scheduler and do some math with modulo and by providing the information how many ranks per node you have launched, and then doing some index math to derive the correct rank. But there's something more robust that you can do. And that is using creating a node local communicator of type by using MPI split type on your communicator using. I used MPI world here, and split by the type type shared, so that you get a subcommunicator for all of the ranks that can communicate via shared memory. And then use that local communicator to query that for a local rank, and then you can use that local rank to handle your GPU affinity. So let me visualize that. So if you have created, done the MPI split for your local com, you get on this 4 node cluster, you get 4 local communicators where all the ranks in the local communicator can communicate via shared memory, and that's the reason why they're on the same node. And the local rank in these communicators is then 0 to 3, which coincides with the GPU ordinals, and therefore each rank can simply call CUDA set device with the local rank. I've added here also a query for the number of devices and added a modulo operation. That's something to make the GPU affinity logic more robust for 2 reasons. First, if you're, for example, in early stages of GPU accelerating your MPI application, you might want to exploit MPI parallelism in parts of your code that did not have yet GPU accelerated, so that you want to launch multiple MPI ranks per node, which works robustly with that. And second, some resource managers might handle GPU affinity for you, so that each MPI rank only sees a single GPU, the one it should use. And in this case, querying the number of devices and doing this modulo operation makes sure that if that happens, each MPI rank just calls CUDA set device 0 as it should. As it might be useful for your own tuning and to explain what a resource manager would in principle do to handle GPU affinity, I've provided an example binding script. This is the output of NVIDIA SMI topo-m, which gives you the system topology of a node from Joule's booster node. And what this tells you is how the GPUs are connected. And in this case, we care for CPU affinity and affinity to network adapters. And you see that GPU 0 has a short single PCI Express switch hop to Mellanox adapter 1, GPU 1 to Mellanox adapter 0, GPU 2 to Mellanox adapter 3, GPU 3 to Mellanox adapter 2. And then these GPU affinity. And then you could write a launcher script, which you prefix for your application that sets some environment variables. First, depending on Snowm local ID, the GPU set CUDA visible devices so that each MPI rank only sees the GPU it should use. Then UCX net devices, in case you use a UCX-based CUDA-AWARE MPI, so that each process also only sees the network adapter it should use and makes sure that every GPU communicates with the optimal network adapter. And last, the CPU affinity, so that the process is mapped to CPU cores that are close in the topology to the network adapter. And after all these environment variables are set, the original application can be used. And something like that are things that the resource managers can do. And for example, the Snowm installation on the Joule's booster does that. So in this case, applications get a very good default GPU, CPU, network adapter affinity, even if they don't programmatically do anything. Okay, with that, I want to switch gears and also want to quickly introduce you to NCCL and how to use that for inter-GPU communication. First, NCCL stands for NVIDIA Collective Communications Library, and it is a communication library running on GPUs for GPU data. So NCCL can work with any data that is GPU accessible. So you could even pass in, you can pass in unified memory into it, you can pass in pinned CPU memory, and of course, device memory, which is the default. All the communication in NCCL is implemented with CUDA kernels. So the communication is always executed on the device, asynchronous to the CPU, but blocking with the CUDA stream it is submitted into. Regarding the data path supported, NCCL effectively supports so far everything what everyone I knew needed. So it can use NVLink, direct peer-to-peer connections, can use PCI Express peer-to-peer connections. It can stage via node local shared memory. It can use sockets. It can use InfiniBand, and also supports other networks. So effectively, the system you're using on should be able to use NCCL. Short overview of the NCCL API before and its capabilities before I go into a concrete example how to combine it with MPI. So you have calls to create communicators, of course, to destruct them. Then the main part of the NCCL, collective communication. And these are closely modeled after the collective communication routines in MPI. So you have send buffers, receive buffers, count, data type, reduction operation, and a communicator. An additional argument in all NCCL communication APIs is the CUDA stream you get there. And all operations, NCCL communicator operations, are asynchronous with regards to the CPU, but synchronous with regards to the CPU stream they are submitted to. That's something to keep in mind. Relatively recently, NCCL also added support for point-to-point communication, so send, receive, so that you can express arbitrary communication patterns. And then there are calls for group start and to aggregate, compose multiple communication calls. And that's something I have an extra slide for. And the idea of that, the benefit of this is twofold. That nickel can works more efficiently in two regards. But the basic idea is that you know that you need that there are multiple nickel communication. If you know that there are multiple nickel communication calls happening that can happen at the same time, it makes sense to tell nickel that. And that is happening by putting them between a nickel group start and nickel group end. While after you've started a group, all communication operations are just enqueued. Nothing is launched. The operations are launched only after nickel group end is done. And that allows nickel to do some optimizations, which improves the efficiency of this operation. First of all, it reduces the CUDA kernel launches for the operation. So it reduces the overhead of scheduling all the communication routines. And it also allows, especially with send-receive semantics, to use multiple NVLinks simultaneously, because nickel knows all the communication that needs to be done concurrently at the same time and does not serialize them. For example, as it is with the nearest neighbor exchange, where you have left-right neighbor and top and bottom neighbor. Yeah, as said, because it's the relatively recent addition is a point-to-point communication, which is best combined with nickel group start and group end, and that can be used to express arbitrary communication patterns, whatever your application needs. So nearest neighbor communication, gather we, scatter we, send receive. So it's effectively everything, everything what's needed to move data without a reduction can be expressed with that, and makes the nickel API very versatile. Okay, so how to use, what about now if you have an MPI program and realize that for certain parts of the code, nickel would provide you a higher performance because of the stream-aware interface, or because it can use the communication path between GPUs more efficiently. And that's a quite non-intrusive space, because nickel can interop with MPI. Actually, it needs something like MPI out-of-bound communication to be bootstrapped. And the way to bootstrap nickel is to first let one participating process create a nickel unique ID, and use the out-of-band communication, in this case MPI broadcast, to MPI to broadcast this new unique ID to all participating processes. And then each process can initialize nickel communicator, passing in the number of processes, the unique ID, and the rank from the out-of-band communication, in this case, the MPI. And after that, you can use that communicator to handle, in nickel calls to communicate with GPU accessible buffers and nickel. And of course, you should clean up after yourself by destroying the communicator if you're done. So the send-receive pattern I have shown earlier for MPI with nickel would look like this. We would have a group start and group end, because all the communication we want to express can happen concurrently. And then we post the receive and send with effectively the same arguments as with MPI. So the type, the destination rank, what we want to receive, where we want to receive to, or where we want to send from, with the communicator. Again, as with all nickel calls, with the stream. One important thing to point out here is that the ordering of these messages is really important in case messages are not unique. For example, if you only would run with periodic boundary conditions, so that the uppermost boundary, the last rank is the top boundary, treated as the top boundary of the first rank, and the first rank is treated at the bottom boundary of the last rank, and you would only run with 2 or less GPUs, then top and bottom would be the same, and the messages would not be distinguishable. And there's a nickel to avoid the overhead. Nickel doesn't have a tag argument in contrast to MPI, so you cannot use that to disambiguate the ones. So you need to be aware of the message ordering in some cases. Okay, before taking some question, I also want to point out how you can combine, how you can leverage nickel from nickel collective performance from nickel from MPI programs without even programming. And that is possible via the hierarchical communication algorithms library, short HCOL, which is a library for software and hardware optimized collectives in CPU and GPU data. So it comes with its own optimized algorithms for CPU and GPU data, but it can also use a nickel backend on GPU data. And it can also leverage hardware acceleration technologies, for example, like SHARP for in-network for doing reductions in the network in the switch. A remark here that HCOL is to be evolved into the UCF project Unified Collective Communications, and a first release of that is expected soon. It's used by HPCX, the MPI implementation shipped by NVIDIA, but it can also be linked by other MPI implementations by linking libhcol. For example, you could configure OpenMPI by linking to libhcol. Showing a bit of performance when first the latency of an 8-byte all reduce from 16 to 512 GPUs. And you see that initially performance between using the plain OpenMPI version, MPI with HCOL or with sharp acceleration is not much different. But if you scale out, HCOL scales much better than OpenMPI, and using sharp provides you an even more stable flat performance. The differences get much larger if you go to large reductions. So here I've chosen to run a benchmark of 1 gigabyte all reduce, some with low precision out of place. And OpenMPI at the bottom is not really competitive because the algorithm implemented there is not at all optimized for large reductions. The HCOL implementations already provide far better performance, but by setting, but you can also leverage the nickel backend to effectively match nickel performance for the MPI collective, and that is this line here, which you see also achieves really nice throughputs, but due to the overhead of scaling this out, breaks when going to. If you also enable sharp, you get the nice benefit of effectively flat performance, irrespective of the number of GPUs you're using, by fully saturating the available network bandwidth. Summing this up, some limitations, unfortunately. Nickel accelerated collectors don't work with MPS. So they don't work if you launch multiple MPI ranks per GPU. And there are also some collectives related to, depending on the threading mode, the communicator you're using, and if you're using non-blocking or blocking collectives, which are listed in this table. Not going to read this. Same limitations will apply to UCC. To enable all this, to enable the nickel HCOL backend is opt-in. So you're and what is required that HCOL can find libnickel.so in your library path, and to set the HCOL _CUDA _bcol environment variable to nickel. And a warning here, these restrictions are not enforced. So if you don't apply to them, you might see weird behavior up to a deadline. Yeah, with that, I thank you for your attention and happy to take some questions and point out some furthermore follow-on material. First, the GitHub repository with with a simple implementation of the 2D JACOBI solver and with using MPI and VSHMEM and nickel. This is also discussed in a GTC talk I have presented at last year's GTC. You can find the recording here. And large overlap with what I talked about, 100% overlap with what I talked about MPI today, but much more content about how to use MPI to program multiple GPUs in a recording of the multi-GPU programming with MPI GTC tutorial. If you have registered for GTC, you can access that recording now under the provided link. If you have not registered, you need to wait a bit longer till it's posted on NVIDIA On Demand. Thank you.
Thank you, Jiri. Thank you very much. While other people think about their question, I have one question to break the ice. So a lot of the material science code are actually written in Fortran rather than C or C++. Can you comment about this programming modeling in respect of, how much they're accessible for Fortran programming rather than the usual C or C++?
There is no difference. I just picked that CUDA-AWARE MPI also works with Fortran and OpenACC. You need to do the same things like using it with OpenACC. You host data use device. If you use standard language parallelism, it uses unified memory. So things should just work. I'm just always picking C++ as the example because my Fortran experience is very limited. So I guess, Felipe, you can even add maybe a bit more to that.
Yeah, no, I just, we are, I mean, it's not our fault, but we often show for convenience because it's also similar to CUDA, can show a bigger picture example in C++, but I resonate very well with the material science community, which is strongly Fortran. And yeah, my experience as well is that everything is the same, especially for Nicole. We provide Fortran interfaces automatically. So it's just a matter of to load the right module and the prototypes are exactly the same. And it's all documented anyway on the website.